Right, it's broadcasting.
Oh, right there. I was like,
So this is Sherwa Wang. He's a graduate student in Oklahoma State University, Stillwater, and he hasn't decided what to study yet. Right.
correct.
So he will be your TA this semester. So he'll be here every Thursday. I won't be here every Thursday. Sometimes I'll be here, but not every Thursday. When the project's starting to roll, what time yet? This time, really. So when the project will starts to roll in a few weeks, and then closing to the end of the semester, I'll be here more often. Any question for Sherwa? I'm sure you will have a lot of questions for him later as we start the labs. So what do we do today? What do you want to do today? I have some program. I have some list of things that we can do. We can review some of yesterday's thing if you want. We can also start learning about assembly language. I'm going to start on that. So the first thing to do is to actually use the download and use the program. All right. So if you go to the class website, let me open the class website. It's HD projector. It's much nicer than the class. Sweet, we can watch Matrix. So if you go to class website, if you go to PLP Tool 5, Java is installed in these computers, but we don't have admin access, right? So when you install PLP Tool, when you go here, are you guys following me right now? So you run the installer. Click on extensions and change the directory to some to your local directory, like we are here. Cool. After you've done that, if you browse to that directory, you should be able to launch plptoolwin.bat. If you're using your own laptop at home, or if you want to bring your laptop here, then you can install as administrator. Right? So if you do that, you can actually go to Start menu. Oops, wrong keyboard. Did you find the PLP tool folder? Can you walk around and make sure that?
So you download it and then run it?
Yes, but when you ask for directory, make sure you pick your home directory. So there should be a list of directories. Click on your username and install there. Otherwise, it won't work. Okay, good. So just put it there.
So how do you bring it up?
So you have to browse to that directory. So you go to your user directory. If you open Explorer, like Windows Explorer upstairs.
I'm trying to get my password back.
If you want to bring your laptop, you can. So you don't have to use it. If you want to bring your laptop to class, go ahead. Because sometimes I lecture with this.
Yeah.
Right, so. Everybody's done? You see the PLP tool window? Now, before we move on, so we've been talking about numbers. Let me switch to camera. We've been talking about numbers and the blocks of the computer. What are they? You have the CPU. What else? What else are there? Memory. Registers inside the CPU. Input/output. So, from the programmer's perspective, how do you actually interface with all these things? So, you've programmed in C and Java, right? How did you actually interface with memory? How did you use memory? Somebody tell me. Charlie.
He said pointers.
Pointers?
But I don't think pointers. I think
When you want to have like a memory space, what do you do in Java or C?
reserve a block.
Allocate.
Allocate? How?
Certain space.
No. Usually when you program, the addresses are hidden from you, right? Even with pointer, it's something that hides the address from you. You don't see hex numbers, right? How do you use the memory when you program in C or Java?
Reserve it.
How about variables? What are variables? Have you ever thought about it? When you say A equals 75, what happens? When you say C is equal A plus B, so you do an A plus B operation, and you've seen the registers and LU, right? So at some point, those two numbers in A and B get to the registers, get added together, and then somehow stored back in C. How does that work? So everything is hidden from you. What the CPU actually sees, you don't know at that point, right? You start running program logically with some algorithm. Say, okay, I want to add these two numbers together and store it here somewhere. But that is hidden from you. But when you go to assembly, that has to be explicitly written. Make sense? So what kind of instructions do you think we need on a CPU to actually accomplish this task? We've seen one from the simple CPU. What was it? The get numbers, right? So the instruction itself has the number. This is called immediate instructions. Why? Because the values you want to use are immediately in instruction. So when the CPU gets the instruction, it doesn't have to do anything else to get the value. Hey, it's already there. I'm going to chop this instruction off. I'm going to use the value. Does that make sense? That's why it's called immediate instructions. Now, what if you want to instruct the CPU to get a value from somewhere else? Is this useful? Yes, right? You cannot encode all your numbers on instructions. Sometimes you need to store 5 gigs of data somewhere, right? You don't want your program to be 5 gigs. In fact, sometimes you need to store something temporarily, which is impossible in the program, right? You don't want your program to be all static. Sometimes you just, oh, I need to keep this value over here for a while that I'll use later. And then we found out that we have very limited amount of registers, right? Let's say you want to store 60 numbers. Even with PLP CPU with 32 registers, that won't fit on the CPU itself. So you have to put it on memory somewhere for a bit. Does that make sense? So this CPU now will have to be able to understand this instruction that tells it to, hey, I need a number from there. Does that make sense? So this is called memory addressing. There are different styles on different architectures on how you access memory from the CPU. But PLP is a load store architecture. What it means, you have all this bunch of instructions, but there's only one instruction that you use to get data from memory, and there's only one instruction that you use to store data to memory. That's why it's called a load store architecture. So if you want to get data from memory, you do a load. If you want to store data back to memory, you do a store. Does that make sense? Is this the only way to do this? No. Other CPU architectures are not load store architectures. They can have instructions that say, hey, I want to add these two numbers together. The first number is here, immediate, but the second number, fetch it from there. So these CPUs have instructions that can fetch things from memory, like in the instruction. Not PLP. PLP, if you want to get data from memory or I/O devices, you have to use load and stores. Does that make sense? So when you get a job and then you have to do Motorola, right? Hey, there's a load instruction, there's a store instruction, but I do not have to do it. I can add two numbers directly from memory. Vera, you're such a liar, right? No, because it's a trade-off. Some CPUs allow you to do it. It'll make the CPU a bit more complex, but it's nicer for the programmer because you don't have to explicitly bring data first, load the data first before you do any operation. You can just single instruction can do many things, not with PLP. To make the CPU simpler with PLP, you do, okay, I want that data. I want to edit with that data. Okay, I have to do load, bring it to the register, edit them together, and store it somewhere else. Cool? We'll talk about this in more detail next week on how memory is addressed. Today, we'll just focus mostly on the syntax of the assembly language, just to get you started on assembly programming. But you have to understand the concept of load and store, of where the numbers come from, where the data is coming from. Any questions so far before we start coding? Okay. Now, let's look at PLP tool. So we've kind of talked about if you hit new, and let me, is that legible? Bigger? Is that good? Turn off the light. Whoa. Can everybody see that? So this is, we start programming in assembly. So who has programming in assembly before? None of you. So this is the first, you have? What architecture?
Using this book. I took this class halfway through 2 semesters.
So 1611.
Yeah.
Okay. So you'll see some differences, right? But the concepts are the same. So what are we looking at here? So we kind of talked about addressing, like how things are addressed, and how things have to be explicitly be said where they are. You can just, whatever. So this is a difference between when you program in high-level language, where something takes care of that for you, compared to assembly where everything has to be explicit. Does that make sense? So when you say A equals 5 on a C programming language, everything, so much is hidden from you that now that you have to dive deeper and see what's going on here. So in PLP assembly, everything that starts with the dot here is a directive. So a directive is not an instruction. So when you assemble this program and you try to load it into the CPU, a directive is a command to the assembler is a command to the assembler. It's not instruction. So the CPU never sees this directive. What the .arc directive does is just basically, hey, okay, assembler, everything below here, start putting all these things from this address. Does that make sense? So in PLP CPU, the memory starts from that address. So that's the beginning of the RAM on PLP CPU. Cool? Any question? Now, how do I get values to the registers? So, like I said before, PLP is a 32-bit system, and all instructions are 32-bit. So, for example, to load a value immediately to the CPU, can you do it in one instruction? let's say I want to load some number to a register. You have 32-bit instructions, and you want to load the 32-bit number to a register. Is it possible to do in one instruction? Charlie said yes. No, Raymond, why? Because you need some bits to what?
Say again?
Why can't we fit 32-bit number on a single instruction to load?
No, I don't
You
know.
got it? What? Why, Charlie?
Well, I'm looking at it, and I'm just looking for the stuff you have here. But
Oh, you're looking ahead.
I'm looking at
Okay.
it down here.
Because the CPU needs some bits of instruction to know what to do. Does that make sense? Right? If the whole thing is the number, CPU is like, okay, so it'll just start executing. And it might not be the number that you wanted to, the instruction that you wanted to execute. Right? So you need some bits on the instruction itself, in the instruction word, that tells the CPU what to do. Does that make sense? So again, in Monday, I'll go into detail about the architecture of the CPU. So it'll make much more sense then. But right now, like, you need some bits to actually tell the CPU what to do. So when you get the 32-bit numbers, it looks at the first 6. Oh, it is this thing. Look at the first 5 bits. Oh, I need to load to this register. And then looks, and then the final 16 bits. Oh, I'll have to load this number to a certain register. Does it make sense? Now, that means to load a 32-bit number, you need to have at least 2 instructions. So the first instruction you can do is load upper immediate. This is the first PLP instruction you guys are learning. Right? So it's load upper immediate. That's the, what's it called, the opcode, right? Now, the first operand is the target register. So there are 32 registers. Register 0 to register 31. Most of them are general purpose, so you can use it for whatever you want. Some of them have special purposes that you learn how to use later in class, or like functions, things like that. The 0 register is very special, though. It's not general purpose. What do you think a 0 register does? It always returns 0. So you can write to it. The CPU will not throw an exception. It's like if you say I want to write to register 0, okay, go ahead. Right? But when you read from it, it always returns 0. What do you think this is? Why do we need a special register that always returns 0? When you program, why do you need a 0?
So you don't get a null reference?
So you know when something's not right?
Yes. So you need something to compare with. You'll find out that you compare with zeros a lot. Does that make sense? So it's pointless to load zeros to register, right? Because you use it a lot. So the designer of the CPU just says, you know what? Since we use the value 0 every 5/10 instructions, we're going to have a register that just gives you 0. So it's convenience. Cool? Any questions so far? Okay, let's use the register number 1. Because since register 0, it always returns 0. Now, in PLP CPU, when you do an immediate stuff, you're only given a 16-bit field. So what range of values can I put in there if it's only 16 bits? What's the answer?
16-bit?
The answer is depends. Now if I say, what range of unsigned integers can I put in here? Now you can actually answer with a number, with a range of numbers. Like what, 0 to, what, 64? 32K? Or 64K? Jera? 16-bit, what's the biggest number? 2 to 16, what's the 16?
64,000, something under.
So who wants to get 64,000, who wants to get a achievement?
I say around 64,000 at least.
64K, so show us a 64K, any? Come on, no guesses? No, don't calculate. Looks like somebody's calculating it.
65,535.
So 64K, you're right. So let's load some number, right? So what have I done? Globe upper immediate. So I have that 16-bit value, I put it on the upper half of register 1. Why upper half? Can anybody guess? How do you load the lower half? Good guess. But since it's a, well, if you are, you pretty much, you're pretty much doing the same thing, right? So if you do this, you're loading the number 48,000 to the top 16, and you load the number 24,000 to the bottom 16. Now this is where things get messy, right? Because the CPU works in bit combination. But if we work in decimal, what will happen to the register after you execute these two numbers? It's just some number, right? Let me show you. So I assemble this. This duct tape assembles the program. What? Okay. So basically what I'm saying, hey, take this, put it on the upper half of register 1, take this, or it with whatever is currently in register 1, and store it back, and write it back to register 1. Does that make sense? If I assemble this and I simulate, and I want to look at, so if you go to this magnifying glass, it will give you the watch window. So basically, with the watch window, you can inspect what the CPU is doing, what are in the registers, and what are in the memory, etc. Cool? And we want to see register 1. So at the start of the program, you have a 0. But never assume this. Most CPUs actually define what the reset values for registers are. So if you go to microchip and look, hey, what are the starting values for the registers? But they're not always 0, so be careful. Cool? In MIPS, everything should be 0. On PLP, everything should be 0. So let's execute this program. Right? After the first execution, whoa, what number is this? 3,145,728. Does this make sense? Why are we getting that number? Because you're shifting it 16 bits to the left. Every time you shift in a binary number to the left, you multiply by 2. Does that make sense? So basically, when you have the number 48,000 and you shift it 16 times, that's the value you get. Any question?
Yeah, how do you get the number to come out like that again?
You step
I'm
through.
getting 0.
You step through the program. So if you look at, click this icon, that executes the first instruction. Cool? So after the next one, now it makes more sense. You add 2400 to it. Well, not add, you already did. This is why we want to use hexadecimal, right? Because it's much easier to read. Now let's change the program. Any questions so far? Or do you see why this is happening? Not yet, huh? Let's do decimal. Let's do a hexadecimal. So let's put hexadecimal dead, right? DEAD. Is that a valid hex number? Yes, it is, right? And beef, the lower 16 bits. Now, if we simulate this, see what happens. When you start the first program, if you look at the hex representation, what do you see? Oh, you can't see, sorry. So you just see that the DAT gets loaded to the top 16 bits. Does everybody see that? Did everybody follow? No? Can you look at Raymond's? So you just get the dead shifted 4 digits to the left, right? And when you OR the beef in, you get that beef in the register. So that's why we use hexadecimal when you want to look at the things inside the computer, because they align with binary, because they're just powers of 2. So when you do a shift and everything, you just see it shifting to the left. Cool? Any questions so far? So this is how you load a value to a register in PLP. Now, to make your life easier, instead of typing out these 2 instructions, so there in PLP tool there's a macro you can use to just so it condenses it to 1 entry, right? So if you want to load that beef into register 1, all you have to do is load immediate number 1 that beef. This accomplishes the same thing. But keep in mind, internally, this is broken into 2 instructions. Does it make sense? So if you execute this program, it'll take 2 cycles, 2 steps to actually get the value. All right? Single cycle, you just get the dead. When you step it again, you get dead beef.
This is a macro.
It's a pseudo instruction, pseudo op. It's not a real instruction, but it breaks into 2 instructions. It's for convenience, right? So you don't have to type LUI or I like all the time when you try to load this 32-bit number. Any question? You will use this pseudo op a lot because you need to load a lot of things to registers. Cool? No question? So now you've done immediate loading. Right? What's the next one? The more fun stuff. Load store to memory. So how do you work the memory? So we kind of talked before, like how program and data are in the same memory. Is that correct? So how do we define memory? How do we define the variable in assembly? So this is where labels come into play. So in assembly, label is basically just a symbol that points to a location in memory. That's it. Is that clear? Let's say we want to have variable A, right? So you can do something like this. Then I want variable A in here. So where's this variable located? So basically, where is this located? It's right after this instruction. So this instruction will be at OR1 all zeros. This will be placed after that. 4 bytes after that, because each instruct, well, 8 bytes, because this is 2 instructions, right? So if you look at the assembly, at the disassembly, if you click the CPU icon here, it'll show you the insides of the CPU. And if you click this assembly, it'll show you where the program is. So at 1001, at address 1, all zeros, you have the load up immediate. At address 1, zeros, 4, you have the OR I. Does it make sense? So basically, whatever you put under the org, it'll just start putting things in order there, in sequence. Any questions so far? Now, what if I want to reserve some space down here? So what you do a dot word. So what I did here, okay, assembler, in this memory location, put this number in there. It become a constant for now. Right? This is basically, you're just saying A equals this on your C program. Does that make sense? You see the connection now? You have to explicitly do this in your program assembly. So if we assemble this and look at the CPU, well,
Can you type notes onto this? Like when we're all done, if we want to do a screenshot and save it to our drive, can we do like / like on
you use pound,
pound?
like the first line here. If you use the pound sign, everything after the pound sign will be commented out. So if you go, we have a visualizer here, right? So here you can actually see what the memory contents are. So if you put in our org, so this is what is in memory, right? So the first one is your load up immediate. So you can kind of see the DET here, the value you're loading. So the first 4 digits are the instruction, the opcode that the CPU will try to figure out what to do. Here, the BIF is here, and this is your variable. Yes?
Can you get to that again?
You go to Simulation, Tools, create a memorizer, visualizer.
Alright.
This will be very useful later when you learn about higher level data structures like stacks, arrays, right? Local variables. But right now, I just want to show you how things are organized in memory.
What's the base address?
The starting address,
Okay.
which is, in this case, just 1 zeros. Cool? Now, you have a variable. How do you access it? At this point, you should be set to go through the first lab that I put up in the website. So Shara and I are here if you need help, but now you have enough tools to actually figure out what to do in the lab. Cool? Any question? Confusion? Lots of confusion?
Yeah, I don't have a clue.
What is your confusion?
Huh?
Like what is, can you say to me like what you're confused about?
I don't even know how to ask.
Like the concept of what? Like loading memory?
I was lost. Figure it out.
But do you understand immediate values? So immediate values are where you have the number you want to load right on the instruction. Right? If you look at this, this is what it means. You're not redirecting anything. You tell the CPU, hey, I want to load this value in register 1. Done. That's immediate. Now, the next step of the lab, that's not true. You're telling the CPU, hey, I want to load something to this register, but you should go over there in memory to get the value. That's a load word. A store word, you're telling the CPU, hey, take this value from your register here and put it over there. That's store word. Does that make sense? Why do we need this? Because we can't encode everything on your program, right? Sometimes you have hundreds of kilobytes of data. When you play a game and you type a document, it will be hundreds of kilobytes. And your CPU will only have 32 registers. You can't fit everything. That's why you have RAM. 2 gigs, 4 gigs, 8 gigs, 16 gigs, whatever. And the CPU needs some way to access that RAM. That's where the load word came from. Are useful. Cool? Yeah. Raymond?
I mean, the task says, the first task for you wants is to write a program that will echo the values of the switches.
No, the first task.
Does everybody else has?
Yeah.
Sorry. Do the load words forward stuff first, and see if you can follow along. Don't do the switches and everything yet. Just do those things and see if you can make sense of it. You know what? Let's do it as a class. Right, let's try to load this variable to a register. I think that's a good start. So, first, if you want to tell the CPU to load something from memory, you have to know where that thing is. This is why it's nice to have an assembler. You can do something like this. Hey, CPU, I know where variable A is. Keep that in mind for now. Okay, where is variable A? Here. What I'm telling the CPU, hey, load to register 1 the location of variable A, not the value of variable A. Does that make sense? This is important. This is where people get confused when they learn C and pointers. You're not loading the value of variable A. You're loading the address of variable A, which the CPU will use later to get the actual value. So there's some indirection there. Now, to actually load the value of variable A, you do a load word. And this is where things get fun. Where do you want to load the value to? Register 2? Sure. And the second part of load word is the address you want to load from, which we know is in register 1. Boom. So this 0 is an offset, right? So if you add 4 here, for example, it will load whatever is in register 1 plus 4. But right now, just put 0. So these two statements, which will assemble to 3 instructions, basically are telling the CPU to load variable A to register 2. Let's see if this is correct. So I'm going to assemble, bring my watch window, and show me register 2, see, right? So at the end of the program, what can you expect? What should the state of the CPU be? What should be the register 2 in the end of the program?
0.
That value. Let's see. So the first step will be that load upper immediate, right? Second step will be the ORI. So now, after the first two instructions, or after load immediate, you have the address of A in 1. Does everybody get that? Now the CPU has something that it can use to point to the memory, right? Now the next step, what should it do? CPU should go to that memory, should get that value from memory location to register 2. So now, if you remember the blocks on your CPU, on your computer organization, right? So now it has to use those buses to actually, hey, grab something from memory. Does it make sense? And the memory will comply, and boom, what you get? Now in register 2, you have that value. Cool? And this is how you use memory. This is very powerful. Now instead of just limited to this 32 registers, now you have 4 gigs of RAM at your command, if your memory is that big. And with 64-bit systems, you can address up to 4 gigs times 4 gigs. So it's like 16 times whatever, really big number. Pretty much limitless memory. Does everybody get that? Load word. Now, after you load a value to your CPU, what do you do next usually? You do what with the data? What's the namesake of the system that you're studying? You compute right? So you get values in and you compute, and what's next? You output. Does everybody agree? You output the result, right? So you get values in, you compute, you output. Now let's do some computation. What do you want to do with this number? You want to do some logical operations? Sure, right? So let's do a logical operation. So when you do operations in PLP CPU, there are two ways to do this. First, you can do immediate operations, which means, hey, I have a value in a register. Do some operation with this value I have in the program. That's immediate. There's also a register operation where you say, hey, I have this value on register 2. Let me get other value on register 4, and then, hey, compute these two values. Does everybody see the difference? So there are two ways to compute. There are two operations. The first one, let's say you already have a value in register 2, this value that you just loaded from memory. Let's say you want to add 1 to it. So the first kind of operation, you just say, hey, CPU, add 1 to it immediately. So the CPU will not have to go anywhere else. Okay, I add 1. The second kind of operation is register operation. What this means, instead of adding 1, adding that register to it with an immediate value, hey, I have a value in register 2. But I have another value that I need to add it with, but I don't have it yet. So you put that value to register 3. Now you have two values, just like the simple CPU example we have. Then you do, hey, add these two together. That's register operation. Is that clear? Right? Because sometimes you just want to add 1 to. When do you add 1 in your program? Do you do it a lot?
Yeah.
Where? Loops? Do you want to access memory every time you add 1? No. Or you just tell the CPU increment, increment, increment. Some CPUs have a dedicated increment instruction. It doesn't have to do anything. It's like, okay, CPU increment register 2. CPU says, okay, that's fine. PLP CPU actually have to provide the number, right? Because we want to minimize the number of instructions. So why use increment if add can do that too? Right? That's the philosophy of the CPU design. Does it make sense? But sometimes you don't have the value when you write the program. Right? Sometimes, oh, I have to take the input from the user. Oh, I have to read the switch if you're working on a smaller controller. Oh, I have to read that sensor first before. Does it make sense? There, you actually have to interface with something else first, and then bring it into register and do operations. Is that clear? Anyone?
Not lost, so you're all right.
All right, but you see the difference.
Yeah, yeah.
Okay, for example, I'll show you the difference. Let's do this, the first case. I want to increment whatever in register 2 by 1. Easy. Well, the add unsigned immediate. So on PLP, except for store word, in PLP, the first register you name is the destination. So let's write it back to register 2. Second one will be the source, register 2. And you want to add 1 to it. Is that clear? So let's simulate this and see what happens. What? Add IU. Add immediate unsigned.
Immediate unsigned.
Yeah. Add IU. Add IU. Add IU. Add IU. Now let's step through this. I got the address. I loaded the value. So after the next instruction, what do you expect to see on register 2? It's what? Incremented by 1. Boom. Yes?
In the instructions you have ADDU. Should that be ADDIU?
IU, immediate. ADDU is different. Which we'll talk about next.
Okay, so just for clarity, that instruction, the first one you tell him to add immediately on the unsigned, And the first one is the register to call. The second
No,
one.
no, no. The first one register that you write to, the destination.
So it's write to, then call.
And then the value you want to edit with. Cool? Now, the second way to do this is to use a second register, right? So if you want to do this, first you have to have the value of the second register. Let's say you have a second variable and you want to add it together. Now, this is where programs get really, now you're starting to appreciate the C programming language, Java, whatever, because now everything starts to get verbose and hard to read. There's a reason why we don't use assembly typically. I want to add 5 to the value, right? So now, how do I get variable B to my CPU? What's the first step? I want to get variable B into my CPU, the value. What's the first step?
Load it in the register.
Load the what?
Load the median,
Of the what? Of the address.
the address, or the, into what register?
So
Like
which,
say $3 var B.
can I use 1?
No, if you do
Why not?
You lose that.
Do I use it again? Did I use whatever in register 1 again after that?
But if you haven't called it yet,
Yes. If you want to use it later, you may want to keep it, right? But if not, you may want to reuse your register. So registers are prime estate. They're fast, much faster than RAM, but they're very limited, right? So the more you can hold, the more things that you use often in the register, the better, because you don't have to go off the CPU to fetch data. That's something to keep in mind, right? So now let's use number 3, sure, and the address of variable B, correct? Now next, what's next? 2, 4, right? And get the address of B. Now into the using add IU, you use add U. So this is a register operation. All the operands are registers. So like add IU, the first register will be the destination, which is what? 5, right? And then you add the registers together. Cool?
That's just adding them together.
Yeah. So the first one will be the destination register.
Mm-hmm.
The second one will be the source. The first source. The third one will be the second source.
How does it know the operation you want to do? How does it know you want to add? Oh, I had yeah.
so
And again, could you say which the first one is the destination?
All instructions except for branches, which you'll learn about, and store. The first one is destination.
So with add IU, you use that just to add a number to
Yeah, immediately add a number to the register.
and add U, you're just adding registers.
Yes. Okay. And you know why you have NIU. Because in for loops, or when you want to increment indexes, you know what you're incrementing with. So why bother getting to memory to get the value? Just add 5 immediately. Now you know why the computer scientists use the word immediate for all this stuff. It does make sense. It's not a misnomer. Cool? Now let's see what happens when you run this program. So now you have a lot more register to watch for. Right. Let's step through. Okay, you get the address of the first variable. Notice how the address it gets incremented for the variable. It changes because you have more instructions, so these variables get all pushed down. You see that? Because the program and data are sharing the same memory. Right? So as your instruction gets longer, as your program gets longer, this gets pushed back. Now my question, is it possible to put the data somewhere else? Yes. Right? If you put another OR down there, you're saying, hey, assembler, get some space between data and program. And sometimes it's useful to do. Cool? Now let's load the number, that number, and then load the second address, which is right after the first one. get the value, which is 5, and after you add them together, boom, you have the answer on register 5. Any questions so far? We're missing one person. I think it's Jennifer.
So register 1 and register 3, the long number you give up, that's just the
Address.
decimal value isn't really anything, that's just the address to where it is.
Yeah. Sometimes it's counterproductive to see the decimal,
Oh, yeah.
right? Now you start to see why we do all this stuff that we talked about yesterday.
Let's not do that.
Unless you want to, like, what's the address of this thing? 4,200,000,000. Oh, shut up. Give me the hex. If you play old-style PC games from the 90s, you know, like the hex editor, where you look at the RAM and start to change values and figure out where's your health variable. You guys didn't do that. Nerd.
Still got that. She did.
So that's what, yeah, that's what this basically does. It scans the memory. You tell it where the program is running, and you hit yourself like in game. So like, what changed? Hey, that's my health. Let's put the FF, full health. There's like a funny. Do you guys play Civilization?
Yes.
Yeah.
So in that game, there's Gandhi. Right? Gandhi is a pacifist, right? So he's supposed to be very peaceful. But for some reason, when his civilization gets democracy, he launches nukes to everybody. It's an Easter egg. Like, why? Why would Gandhi launch nukes to everybody? At this point, it's a joke. But on the original Civ 2, which I played, I hated Gandhi. In-game Gandhi. I don't know him enough in real life. But so what they do, they have a variable that denotes how aggressive they are with nukes. Gandhi has it as 1, right, which is the least aggressive. The problem is, when you get democracy, you have a modifier to this variable by 2 or something. When applied to Gandhi, you decrement -2, 1, you ran out of space. It rolls over to 255. So once he gets democracy, he just nukes everybody else. Like, whoa! And then the developers just realized it was so hilarious they kept it in until Civ 5. Cool. Any question? That was such a nerd reference, but I thought it was funny. And it's relevant to our field, right? Rollover. Dangerous. What do you think the year 2000 bug was? Same thing.
I do have a question. So in the stuff that we've done here, I've commented it so that I can understand it. How can I'll be done. Where can we call this from?
What do you mean?
Where did this file get saved into?
So if you hit save,
Yeah, if you hit save, it gives you the option to.
yeah, just save it somewhere.
So where?
Well, it saves it to whatever directory you save it to. Yeah.
That's what you. Yeah. So if we had a flash drive, I could save it.
Mhm.
It left my flash drive.
Probably just send it to your computer or something.
You got a Dropbox?
Yeah.
Save it to Dropbox. Save it on the desktop, like your Dropbox.
You're not banned from Dropbox.
What the heck are you sharing, bro?
I work at that permission to Dropbox.
Oh, in here. Oh, email it to yourself.
Save it, yeah.
Or email it.
Such
You don't have to
old-fashioned
download
way to
Dropbox.
transfer data.
I'm saying if the website is wrong.
Clock with weight. So now you've done computation, right? So what's next? What do you want to do next? So you process things and what?
So for all the commands, I mean, they're like sub-U for subtract.
So for those things, if you hit F1, it tells you what commands. If you're curious of what the CPU can do. Any questions so far? Well, you do have questions. Sounds good? Everybody's on the same page? Load immediate, load word, some computation, immediate versus register. Everybody get that? Good enough. Right. So what's next? you have a result in the CPU, right? You can't just open your computer, look at the CPU, hey, I get my number. What do you do next? Output. Where do you output? Screen or LEDs. For now, let's output to the memory bank, right? So this is where store comes in. He was never here. So let's have a third variable, key, just 0, and we want to store the value here. Guess what the opcode for store word is? It's not very creative. SW. Right, SW. Now, store word is unique in that the first argument, the first operand, is the source register. I kind of hate this, but that's how they do it. So where's your answer? Register 5, right? Wait, what did I miss? What don't I have? What I don't have? Do I know where varc is yet? Does the CPU know where the... Do I know the address of the destination? No. Right, so I have to, again, so on the simulation, you can actually watch memory spaces. So let's bring the watcher here.
What did you make variable C?
Just 0. So I want to watch register 6. I also want to watch variable C. Right. So now we know that var C is at this location. Any question? So you can watch both memory space and registers in this window, which is pretty useful. Now let's do this. Get var A in, get var B in. So I have the two operands. Add them together. Have the result. Get the address of var C and the store word to put the value in this space. Boom. Now the CPU has gotten some value from memory, do some computation, and store it back to memory. Any questions so far? No? Yes?
What is that last one?
It's a location. So if you go to bus and then put in the label, like var C, it'll watch that memory location. So in Monday, we'll talk about in detail about the memory addressing part. So this is the programmer's part. And we learn why everything is enforced. Sure.
Well, okay.
You haven't defined parts yet.
So I'm going to defining a merge define whatever that means. And then you're going to tell it that you want to load immediately 6 var C, which is 0. But then you turn right back around and you want to store the address.
No, this is what store word is different. Store word is our store word. Yeah, number 5. Store it to wherever point 6 is pointing. So 6 at this point have the address of var C. Right. So when you do this math, this instruction, you're telling CPU, hey, get whatever is defined, give it to where 6 is pointing.
Okay, and so wherever 6 is pointing at C. So C, how can we find out where
Plus var C values, that's where the assembler comes in. Right. It's possible to actually system tell where
This.
So you just hitting them.
So this,
Whatever you much divide.
Oh, okay.
Same
Yeah.
thing.
All right.
it's just much nicer to actually just refer to
Yeah. All right.
because as you change your program varsity years.
So if you wanted to see what was in varsity, you could
Yeah.
create another register. And if you wouldn't need to do that.
Okay.
But if you as an individual wanted to see, you can create another address, register it, and follow RC after you've done that to see what needs to zero.
Yeah, you can load it back.
Okay, so now
Yeah.
it's offset. So like, so say like stuff version. The version
Yeah, it's been a year since I've heard
It's
It's not the same number. It's like,
Always use the label because the label is given the right.
Yeah.
Oh,
yeah.
It's like it's a offset zero.
yes,
Right.
So what was it?
Yeah, but a quick.
It's for convenience. Now, let's use switches and LEDs. Let's have some human interaction. So basically today you guys get all 500 points for free. Have a great first week. Yay! Hey, you learned things, right? Yeah. Hopefully. You better. Now, how do you interface with things like switches and LEDs and ports? So this is where the concept of memory mapped I/O comes into play. What do you think memory mapped I/O is?
Address to an input or output port.
What's your name again?
Larry.
Larry. Correct. That's it. So you treat I/O devices as memory locations. This is very, very common. When you go to work and you work with PIC, you work with Atmel, you work with whatever, this is how you do it. Let's say you're designing an ECU for a car. It uses what, CAN bus. How do I talk with CAN bus, right? Oh, it turns out it's memory mapped I/O. I just look at all these registers and do stuff. Same thing. Cool? The simplest concept will be like a LED. So if you look at here, so the PLP CPU is hooked up to an array of 8 LEDs. And the physical connection is abstracted away from the programmer. All the programmer needs to know, the LED has an address, and the bottom byte of the value in that address will correspond to whether the LED is on or off. Does that make sense? Is there any other way to do this? Do you think there is other ways to memory map I/O?
Yes.
Yes, of course, right? Now I know here. When he's asking these things, there are. But watch out. Sometimes there are. Right? So, yes, sometimes you have spatial instructions to access I/O. x86 has I/O instructions, but they are obsolete now. So basically, you're saying to the CPU, "Hey, CPU, load this value to I/O 1." The pros and cons are, if you have instructions just to do I/O operations, you free up the memory space, right? So you free up some addresses for pure memory instead of I/O. The disadvantage is the CPU will be more complex because it has to handle all these I/O instructions. For convenience's sake, nobody barely uses any I/O instruction anymore. Cool? It's still there for legacy purposes, but many new controllers just use memory map I/O. Any question? All right, so LEDs. I have an address. See how nice it is? So you just have an address, and if I store a value to it, it should give me some nice looking LEDs, right? So let's load some values. What do you want to load to the LEDs? Well, first, get the address of the LED in your CPU. If you press F1, it should bring up the quick reference card, which will tell you all the instructions and where the I/O is. So it's help quick reference. So LED is at 0xF0200000. Right? Boom. Now I have the address of an LED. Everybody get that? Now what value do you want to output to the LED? So PLP tool accepts binary. You can do something like this. So 0B denotes a binary representation. Right. So now in register 2 we have this 1 byte. So when you just provide the 1 byte, yes, Raymond.
Okay. Yeah, so if the LED is either on or off, can you input any number as long as it's not 0 and turn the LED on? Or does that be 1?
This is a possible Zen moment for everybody. Ponder on your question for 5 seconds. Digital. It's digital.
But to me, it seems right. It should be digital. So 0 is 0, and anything else should be a 1.
There is no anything else. There's only 0 and 1 for each location, for each digit. Zero means LED off. That LED is off, like this. 1 means that LED is on. The next digit will be the next LED.
So it's just a single bit?
Yes, per LED.
I thought we were sending it like a byte instruction.
It's a byte array. So the LEDs are only 8, right? The CPU is 32 bits, but only the bottom 8 gets hooked up to the LED. Probably that's what's confusing you. Just watch, right? So I have the address of the LEDs. I have the values I want to output to the LED. What's next? How do I store it to the LEDs? What instruction? SW. What's next? Which register? To the source, and then the address, right? When you simulate this, you can bring up the LED, right? So first you get the address, you get the value. Now, after I execute the next instruction, I should get it to light up, right? So if you look at the binary number, they match with the LEDs. Cool? This is a very common operation to do, like trying to output and flip an LED or read a switch. You see this a lot in your devices, right? You have a button or you have like a display lights to tell your monitor, your computer has it. So.
Yeah, see, I thought when you were loading that binary number, I thought that binary number was to control a single LED, but if it's to control all 8 of them.
Yeah, so it's parallel.
That's easy.
Okay, now read from the switch. I'll let you guys do it. So your task now the lab assignment makes sense, right? So your task now is to read from the switch and then mirror it to your LEDs. Cool? Yeah. Have fun. I'm going to stop the broadcast. So if you miss anything, I'll put it up on YouTube again.